Artificial intelligence stands at the edge of becoming humanity's most transformative creation, a technological leap so profound it could redefine science, consciousness, and the very nature of reality. Yet for all its potential, AI faces an existential bottleneck: power. Not influence or control, but raw, unrelenting electricity. The most advanced AI systems today consume energy at rates rivaling small nations, and as they grow smarter, their hunger for power grows exponentially. The question is no longer whether AI will reshape civilization, but whether we can even afford to keep it running. The answer may lie in the most controversial yet undeniably potent energy source ever harnessed: nuclear power. To grasp the scale of the problem, consider the world's most powerful AI supercomputers. Elon Musk's xAI recently unveiled Colossus, a monstrous machine built in Memphis, Tennessee, housing over 200,000 NVIDIA GPUs. Interconnected by high-speed server racks and cooled by a staggering 100,000 gallons of water, this system powers Grok, Musk's unfiltered high-performance AI chatbot. Colossus devours 125 megawatts of continuous electricity, equivalent to powering a mid-sized city like Asheville, North Carolina. And this is just the beginning. Musk has already projected scaling Colossus to 1 million GPUs, pushing energy demands beyond 500 megawatts, nearly half the total power consumption of Memphis itself. But xAI isn't alone. Google, Microsoft, Meta, and Amazon are all racing to build ever larger AI models. OpenAI's next-generation systems will demand even more power. If this trend continues, AI could soon consume double-digit percentages of global electricity, a scenario that would overwhelm existing power grids and make fossil fuel reliance unsustainable. Renewables like solar and wind, while crucial for a sustainable future, simply can't meet the 24/7's high-density power demands of AI data centers. Solar farms require vast land areas, 11 square miles to match the output of a single nuclear reactor, and are intermittent. Battery storage solutions like Tesla's megapacks help but can't yet bridge the gap for terawatt-scale AI operations. Nuclear power, however, offers massive energy density. A single reactor can generate 1,700 plus megawatts, enough to power multiple AI supercomputers in surrounding cities. It provides zero carbon emissions, unlike coal or natural gas, and runs non-stop regardless of weather. Despite public fears, nuclear is statistically one of the safest energy sources, with fewer deaths per terawatt hour than solar, wind, or fossil fuels. Microsoft recently signed a deal with Helion Energy, a fusion startup, aiming to integrate nuclear power into its AI data centers by 2028. Google is exploring small modular reactors to directly power its server farms. Even OpenAI's Sam Altman has invested heavily in nuclear ventures, recognizing that AI's future depends on unlimited clean energy. Meanwhile, Tesla's energy division could play a key role in stabilizing nuclear-powered AI grids. Their megapack batteries could smooth out power delivery, ensuring supercomputers receive ultra-stable electricity without fluctuations. If AI can break free from energy constraints, the implications are staggering. AI could simulate quantum physics, molecular biology, and climate systems at unprecedented scales, leading to breakthroughs in fusion energy, carbon capture, and materials science. Drug discovery could accelerate 1,000-fold, with AI designing cures for cancer, Alzheimer's, and aging itself. Space exploration could be transformed, with AI optimizing spacecraft and solving interstellar travel challenges. Brain-computer interfaces supercharged by AI could merge human cognition with machine intelligence. The U.S. power grid is already strained. In states like California and Texas, blackouts are becoming more frequent. The grid, as it stands, can only handle a 20 to 25% increase in demand before risking systemic failure. Yet AI's power needs are growing exponentially, not linearly. If every major tech firm builds its own colossus, the grid will collapse without a radical energy overhaul. This isn't just about computing, it's about energy dominance. The companies that secure nuclear-powered AI infrastructure first will gain an unassailable advantage in the tech landscape. Governments are taking notice. The US and China are already investing in next-generation nuclear reactors to support AI and supercomputing. We're entering an era where AI won't just be limited by algorithms, but by megawatts. The nations and corporations that solve the energy problem will lead the next century. Nuclear-powered AI isn't science fiction, it's an inevitability. The fusion of unlimited energy and super-intelligent machines will redefine what's possible, from curing diseases to exploring the cosmos. But this future hinges on one critical factor. Can we build the energy infrastructure fast enough? If we succeed, the 21st century could see advancements that dwarf all of human progress combined. If we fail, AI's potential may remain forever locked behind a power barrier. One thing is certain, the race to power AI will reshape civilization itself. The question is, who will control the reactors that fuel the future? The race to solve AI's energy crisis is already underway, with tech giants and governments scrambling to secure their place in this new energy landscape. Microsoft made headlines by hiring a director of nuclear development to oversee their atomic energy strategy, while Amazon recently purchased a data center campus adjacent to a nuclear power plant. These moves signal a fundamental shift in how we think about powering the digital age. What makes this transition particularly urgent is the accelerating pace of AI development. Each new generation of models isn't just incrementally better, they're exponentially more powerful and consequently more energy hungry. The AI systems we'll see in the next 3 to 5 years could require 10 to 100 times more power than today's most advanced models. This isn't sustainable with our current energy infrastructure. The nuclear solution presents its own challenges that must be addressed. Public perception remains a significant hurdle, with decades of nuclear skepticism to overcome. Regulatory frameworks need modernization to accommodate next-generation reactors. And perhaps most critically, we need to train a new generation of nuclear engineers and technicians to build and maintain these systems. Yet, the potential rewards justify the effort. Imagine AI systems that can run continuously without energy constraints, tackling problems like real-time climate modeling that predicts weather patterns months in advance, medical AI that analyzes entire human genomes in seconds to personalize treatments, material science breakthroughs that could lead to room-temperature superconductors, advanced physics simulations that might unlock the secrets of dark matter. The infrastructure being built today will determine whether these possibilities remain science fiction or become reality. Data centers are being redesigned from the ground up with nuclear integration in mind. Some futuristic concepts even propose embedding small reactors directly within computing facilities, creating self-sufficient AI hubs. This nuclear AI convergence could also reshape global power dynamics. Countries with advanced nuclear programs may gain significant advantages in the AI race. We're already seeing nations like France, China, and the US position their nuclear capabilities as strategic assets in technological competition. As we stand at this crossroads, one thing becomes clear. The future of artificial intelligence is inextricably linked to the future of energy. The decisions we make now about powering our AI systems will echo through the coming decades, potentially determining whether we enter an era of unprecedented technological abundance or face artificial limits on human progress. The nuclear option, for all its complexities, may be our best path forward into this bold new world.